So a little bit of review of creating pattern equations. So if you have something linear, how do we know something is linear, first of all, if we have these numbers?
It goes up by the same amount.
Which
or
is
goes
what
down.
here?
3.
It goes up by 3 every single time. So it's like the first difference is the same. So with linear, we know we can create a linear equation. From grade 9, you did y equals mx plus b. You've also learned maybe this other version of the linear equation, which you could use here. Or because this is sequences in grade 11, you would have learned the term formula, which in my school we use Tn, but all the resources here use An for the sequences, so I'll stick with that. And then you'll have first term, which we'll call A1, plus the difference times, do you remember what?
N minus 1.
N minus 1. So because this is a sequence type of question, let's do this for this question. What's the first term?
37.
What's the difference?
3.
And then n minus 1, and then you can either leave it like that or simplify by expanding and collecting like terms. So it would be 3n plus what number?
34.
Yeah. And so that would be your equation for the linear type. Let's move on to another type. So we call this linear, but we also call it arithmetic sequence. Now, quadratic cannot be called arithmetic or geometric. It is neither one of those. It's a quadratic version. So let's talk about how to create a pattern. And first of all, how do we know it's quadratic type? So first of all, here you're going up by 0, here by 4. Next one by, help me out.
By 8.
And then?
16.
16 over here. Before that?
Oh, that's 12.
Yeah, and then one more.
And that's 20.
Okay, so first differences are not the same, so we know this is not linear or not arithmetic, but there's definitely a pattern, right? What is the pattern of the pattern, or second difference?
You add 4.
Every single time, right? So because it is quadratic, you can create an equation for it using a pattern for quadratics. There's several ways to do this, but I'm going to give you a method that will work easily even with the next one we'll do, which was cubic, okay? So for any type of polynomial, if it's a perfect polynomial, you can apply this. We'll create a table with n, or positions, as the first column. And then the other one will have our sequence, which, because we know it's quadratic, we'll create an squared plus bn plus c. And our goal is to figure out what is the a and the b and the c in this equation, kind of like ax squared plus bx plus c for quadratics, right?
Okay.
So we'll stick 1 in at the beginning. So we're putting into this relationship a 1 for the n's. Do you agree this will be a plus b plus c?
Yes.
Let's do 2 as well. Do you agree this would be 4a plus 2b plus c?
Yes.
Let's do one more, because we have 3 unknowns. We need 3 points to plug in. So tell me the next one.
9a plus 3b plus c.
Okay, very good. So now what we're going to do is we're going to do differences. So if you did in grade 9, you had x and y table, and then sometimes you did like changes in y or the differences in y. For the slope, for example, you did difference in y over difference in x. So that's what we'll do here. We'll do differences in our outputs, okay? So from here to here, if you were to subtract this line and then minus this line, you'll notice that c's will disappear, and 4a minus a will be my 3a as a difference, and then 2b minus b will be just a single b. Do you follow so far?
Yes.
Let's do the same thing with this one on the bottom minus this middle one. Also, c's will cancel, but what will be left?
That would be 5a plus b.
Okay, then we're going to do a second difference. So a difference of the difference. From here to here, what's the difference? B's disappear.
2a.
Wonderful. So the reason why we did that is because now, instead of solving 3 equations with 3 unknowns, because we don't know A, B, C, and you could do it by process of elimination. You can work with 3 equations, eliminate 1 variable, then work with 2 equations, 2 unknowns, and then continue eliminating. But I find this, what I'm showing you right now, is a little bit faster. I'm going to take this 2a, which is a second difference, and I'm going to take this 4, which is also a second difference. Do you agree? I'm going to make them equal to each other. This is an equation that has only a single unknown. Can you solve for a for me?
A equals 2.
Wonderful. So then I'm going to take this first difference, and make it equal to the first difference here. So I could have done that, or I could also take this one if I wanted to and compare it to the second value of the first difference. Your choice, really doesn't matter. So I'll go with the first one. 3a plus b is equal to 0. Do you agree we can plug this in and solve for b?
Yes.
So that would be 3 times 2 plus b equals 0. What's b?
-6.
Okay, so finally, we still don't know c, so take one more. It really doesn't matter which one you choose. I'll take the first one, and I'll take the first one from here. Create an equation. A plus b plus c equals 1. A is 2. -6. C equals 1. What's c?
That would be 5.
5. And therefore, our equation would be 2n squared plus, well, actually minus 6n plus 5.
Okay.
Right? And then you can verify. I would always double check that what you got is okay. So I'd go, okay, that's 1, 2, 3, 4, 5. Let's just choose a random one. So this is where n is 5 and sub in. So n equals 5. You'll have 2 times 5 squared minus 6 times 5 plus 5. Do we or do we not get 25? We should.
That's 50 minus 30 is 20 plus 5. Yeah, 25.
Yeah, so this method works for quadratics. And then for cubics, it does a similar thing. You can come up with same idea, except this time you're going to go a little bit longer because you're going to have to do second difference. This is first difference, second difference, and then you need to do a third difference. And then when you're creating a cubic, you'll have A, B, C plus an extra D because your power will start with a power 3.
Yeah. Okay.
In preparation for this one, I actually did this already somewhere. So I'll just take a picture and stick it in and just spend a little bit more time on something that's different, okay? So just a second. All right, so here's the example for the cubic. You can see it is a very similar way to work with it. Instead of working with 4 equations, 4 unknowns at once, if you decompose it into the differences here, which I call the difference of y instead of difference of the term, but whatever, it's just the output, and then just compare, whichever one you were taking to the first one of each column, then you should be able to find your A, B, C, and D to create an equation for the cubic, if there was a cubic pattern. So are you okay to move on to an exponential type?
Yes.
So with exponential, first of all, how do we know it's exponential? What's the pattern here?
It's multiplied by 2.
Mm-hmm. So with exponential, we had 2 ways to do this. When we were studying exponentials in grade 11, I think you would have created some sort of equation that would have a coefficient, maybe some sort of base, and then some sort of power. Or when you were studying sequences, you would say it's a geometric sequence, right? And you would say Tn, or I'll use An again, where we had the first term, then the ratio, and do you remember the power?
N minus 1.
N minus 1, because n is position and never starts with a 0, it starts with a 1. So let's do this version here. So An, what's the first term?
6.
And then ratio
is 2.
And then you'll have n minus 1. So you either leave it like that, or you could say This is power n, and then this is 2 to the 1. Do you agree when you divide same basis, the exponents subtract?
Oh, yeah, yeah.
And then you could change it to be just 3 with 2 to the n if you wanted to.
Okay.
Right? So that's a way to recognize exponential or geometric series or sequences. What you may not have seen is this one. So I do this with my students. I'm wondering if this would be done if you've seen something like this. So when you're looking at the pattern here, what would you say is the pattern? Do first of all differences to start. How does it go up by? Plus what?
Plus 3.
Then
plus 6.
Mm-hmm.
Then plus 12.
And
then plus 24.
Okay, so there is definitely pattern in these numbers, right? What's the pattern when you're looking at these?
Multiply by 2.
Mm-hmm. So as soon as you have multiplication by 2, you know it's something to do with an exponential, but because the ratios are not the same right away, there's as if there's some sort of shift. So you can create an equation for it using what we talked about with exponential from before, like the basic one, except you can add some sort of shift. Let's call it plus c here. So let me show you how you could create an equation for that. I know I'm using y and x instead of n and an, whatever, it doesn't really matter. Input, just remember that x starts with 1 if you're thinking about x's. Just like with n, the position always starts with 1. So when you're doing this, I would suggest, because we just have a, b, c, it's not too hard to just use the points. So when you're thinking about points x, y, think 1 for the n, if this was n, and the output of the value would be the 2, right? So if you put that in, you would have a times b to the 1 plus c, right?
Yes.
Let's do the next point. If you were to use second value of position, which is value of 5, that will give you 5 equal to a, what else?
B squared.
Mm-hmm.
Then plus c.
Plus c. So at this point, we still need a third point as well to use, but we can maybe eliminate the c's because it's plus c here. So what if we were to subtract these two equations? So let's do 5, subtract a 2, you get a 3. Then ab squared minus ab, they're not like terms, so I'll deal with it later. I'll just record this. And then c subtract c is gone.
Yeah.
Okay. So then, because we do have a and b and c, we have actually 3 unknowns. So let's do one more point. Let's plug in 3 with what?
11.
11. So that would be 11 equal to ab3 plus c, right?
Yes.
Let's do another subtraction. Really doesn't matter which one. So you could do these two. Let's subtract again. What's 11 minus 5?
6.
And ab3 minus ab squared, and c's disappear again, right?
Yes.
Okay, so now instead of having 3 equations, 3 unknowns, we have 2 equations with only a and b. There is no more c's. So what can we do to start isolating some, either a or b? What do you think we can do there?
Can we divide?
We would be dividing, but maybe before dividing, let's factor.
Oh, yeah.
What do you get?
That'd be b minus 1.
Okay, and then do the same thing here. Factor. ab squared is common.
And b minus 1.
Okay, so to eliminate this time, because they're multiplied, we will divide. Again, we'll do bottom divided by the top. So 6 divided by 3 is
2.
a divided by a is gone. B squared divided by b is
B.
And then b minus 1 divided by itself is gone as well, right?
Yeah.
So we just found the b, which actually we didn't really have to do that. We knew it was multiple by 2. That could have been your base to start with, right? Because we knew the pattern is multiple of 2. Anyways, in case you didn't notice that, you could just continue solving like that. So now that we have the b, you put it back into one of the equations to find the a. So don't go all the way to the beginning where you had b and c. You want to backtrack just one step so that you're introducing one variable that's extra at a time. So you'll have 3 is equal to, let's use the one over here. A we don't know, b is a 2, and then 2 minus 1. What's our a then?
3 over 2.
3 over 2, I'll circle that. And now that we have a and b, then we can put it into that one, or any one of the 3. I usually choose the first one because the numbers are smaller there. So you have 3 over 2, multiply the 2 plus c. What is c then?
-1.
-1. And so therefore, let me convert it to the terms. So instead of y, I'll use an. Instead of x, I'll use the n. So a is 3 over 2. Base is 2. Exponent is n. And then -1.
Okay.
So that's a way to develop a pattern like that. And of course, always check. Just double check. So if it's 1, 2, 3, 4, 5, this one's the 5th one. So n equals 5. So let's plug in 3 over 2, 2 to the 5 minus 1. 2 to the 5 is 32, right?
32, yeah.
Divide that by 2.
That's 16.
Okay, 16 times 3.
20 times 3 is 60 minus 12. That's 48.
And minus 1?
47.
Yeah, it works, right?
Yeah.
Okay, so then in the unit that we're studying right now, it's not just sequences. Instead of a list of numbers, we're studying series, which is, remind me, instead of a list, it is?
Like a summation.
A summation, yes. So let's also review partial sums. So I know in grade 11 you were told the partial sum formula. Can you tell me what it was, if you recall? But then I'll show you how it came to be.
It was n over 2.
Yeah.
And then times the bracket a plus d times n minus 1.
So close. You're missing a 2 right there.
2a. Okay.
Let me show you where it came from. So when somebody actually, I don't know if this story is true, but I don't know if you read about mathematician Gauss. When he was a child, I don't know how true the story is, but some sort of teacher gave busy work to the children and said, please add up from 1 to 2, 3, all the way to 100. And back when he lived, there was no calculator, so they had to do it by hand. So he thought he's going to keep the kids occupied. But this genius child came back to him very soon after with an answer. What do you think he did?
Did he reverse the order and then get
Yes. So sum of 100 terms, he reversed the order. He put 100 and then 99 and then 98 and then blah, blah, blah. 3, 2, 1. So you reverse the order. And what's the trick here? What happens now?
You add the 2 together.
So you'll have 2 of these sums, right? And what do you get every single time as you add these 2?
101.
And then if you add these 2?
101.
And you get the same number how many times?
50 times.
Think again. How many terms do we have?
Oh, yeah, 100 times.
100 times.
Right.
Right? And so in general, Sn, right? So the 100 here will represent how many terms we're doing. It's going to be found by multiplying by n. So 100 times is how many terms you have. This 2, we need to divide out. So that's where the n over 2 comes from in the formula. Do you see that? And then in terms of the rest of it, well, think about it. This first term is the a, or a1. This 100 term is the an itself, the last term, which has a general formula a plus d n minus 1.
Oh,
right?
okay.
So you have a that's added with another a plus d n minus 1. That's where the 2a comes from.
Okay.
Right?
Yeah.
So that's a sum for specifically arithmetic sequence. I don't know of a trick for quadratic, to tell you the truth. Like when I was preparing for this to see if I can come up with a, partial sum for quadratic patterns. So this was 1. The second sum would be 1 plus 1, which is 2. The third sum would be 1 plus 1 plus 5. So that's a 7. I couldn't come up with a way to do that. So I'll just show you the exponential one as well, because for that one, definitely there's a formula for it. First of all, do you know the formula? And I'll show you where it comes from again.
It was a times r to the power of n minus 1, and then
all over something. R minus 1.
R minus 1.
Yeah.
Okay.
So I'm going to show you where that one comes from as well. And if you think you can develop something for the other ones, please let me know. I didn't have time to Google. Maybe there is such a thing that's, some sort of trick to get those to work as well, because that would be useful if we can come up with, anything that we encounter. But anyway, so let me show you the trick for this one. So for explanation of that one, let's do a simple one. Instead of the pattern that we were developing, let's just use, let's say, a pattern of 1. Then you multiply that by 2, you get 2 plus times 2 again, times 2 again, and then dot, dot, dot. And at the end, I'll just say it's going to be the formula. So 1 times 2 and minus 1, whatever that is. Is that okay? The last term. So let's call this Sn as the sum of n terms. The trick here is, instead of reversing the order and then adding, the trick is to multiply this by the ratio. So for us, the ratio is a 2 of the sum. So when you're multiplying by the 2, I'm going to actually record this slightly to the side. 1 times 2 will be the 2. And notice how that 2 with this 2 will align. We'll do that something with that in a moment. Then this one multiplied by 2 will give you the 4, etc. So this term right here would be the 2 with just an n, and the one in front of that would have been this 2 with n minus 1. Do you follow so far?
Yeah.
What do you think we can do after this trick?
Could we subtract the 2?
That's right, we will subtract, because once we subtract, all the center terms disappear. So we'll have this 2Sn. Technically, let me write it down in general. This is like the Rsn minus the original Sn, right? We're doing the bottom minus the top is equal to -1, because we're subtracting this one. And the only other term left over is this 2 to the n. But let me make it general. First of all, this 2 to the n is your a, Rn minus 1, the previous term, multiplied by an extra r. So in general, this would be, let me record, -1 plus a r to the n only, right? Do you follow?
Yes. Yeah.
And so next line, we can factor Sn out of this. R will be with what?
-1.
-1. Oh, and by the way, this 1, I should have said this is not just a 1. I should have called it an a, because it could be any term that we're starting from, correct?
Yeah.
So let me just change this to be -a. And on this side, we can factor out a, and we'll get r to the n minus 1. And then you can see how the formula comes to be.
Okay.
All right. So I think this will be useful anytime you see a pattern, just to have some more tools in your bucket to pick out to figure things out. Just keep in mind that it's not always possible to find a formula.